Yeah, so we always in math have to start with a definition. So the definition that we start with is the derivative of e to the x, okay? And the derivative of e to the x is just, by definition, e to the x, okay? That's how we define e, and then we derive the number e based on that definition, okay? So once we have the derivative of e, what if we want to find the derivative of a to the x, where a is not equal to e? Well, there's one thing that we can do. We can move from the derivative of e to the x to the derivative of a to the x using the fact that we can rewrite a to the x. So a to the x is equal to e to the log, or let's use ln, not the log, e to the ln a to the x. Again, this is this definition. And then using the standard log rules that we looked at last time, we can rewrite this again as e to the x ln a. Okay, so can I get F's in the chat if everyone's happy so far? Good. 19 people and 9x, 10x. What's up with the other 9 people? Well, I guess 7. Okay. Well, ask if you're confused. So, right. So then we can rewrite this as e dx e to the ln a times x. And now all we have to do is use the chain rule. So before I go any further, let me remind you the chain rule and the product rule. So the chain rule says that if you have a function f g of x, and we take its derivative, then we end up with f prime g of x times g prime of x. And the product rule says that if we have e dx fg, these are f of x and g of x, we get f prime x g of x plus fx g prime. Okay, so we use the chain rule here, and using the chain rule, we take the derivative of the outer function. And the outer function is just e to the x ln a. So we get e to the x ln a, and then we take the derivative of the inner function, which is x ln a, and we just get ln. Okay, so then we can do another simplification. This part is just equal to e, or is equal to x ln a, which is equal to ln, sorry. This part is equal to a to the x. So then we end up with a to the x, and that's your formula. Okay. So hopefully everyone's happy with this. Oh, f okay, good. Yeah. Okay. Thank you. Putting F in the chat. Are there any questions? No. Okay. Fine. So let's do a couple of examples. The first example is easy, and the second one is hard. So in your breakout rooms, which I'm about to put you in, give these two problems a try. Two is d dx a d. And if you look on my notes, you'll see some hints. So I'll also put the link in my notes. Okay, now let me put you in your breakout rooms. Yeah, so we'll go over these. Oh, can people hear me? Can people hear me? Hard to hear. Okay. Let me try this. Is this any better? Can people hear me now? Oh. Okay. Great. I don't know what the problem was. Let's. Oh no, my computer is freezing again. Ah, this is the problem with an 8-year-old computer. You can do it. All right, so let's go over the first one. So the first one, two things are involved. First is the derivative of an exponential function, and the second is the product rule. So let's do it. We take the derivative with respect to the first term, and then we just get, by the formula that we just derived, 2x ln 2. And then the second term stays the same, so x plus 3 with x. And then we multiply by the second term, or by the first term, and take the derivative with respect to the second term, which just gives you this. Okay, so hopefully everyone got that. F's in the chat. Yeah, cool. Thank you. Okay, so for the second one is a little bit trickier, but hopefully if you followed my hint, it didn't go too badly for you. Yeah, great. So what we do is we rewrite this again as e to the ln a e to the x, and then we can rewrite this as e to the x ln a. And now we can take the derivative. So if we take the derivative, we get, okay, the outer function is just e to this thing. So we just get e to the x ln a. And then we take the derivative of the inner function, which is b to the x ln a, and we get e to the x ln b times ln a, where a and d here were just constants, right? So then what does this give us? This gives us a to the b to the x times b to the x times ln b times ln a. So this is a good example of why it's kind of a bad idea to memorize a formula, because if you memorize a formula for this thing, then you're able to solve the basic case where you're only raising it to 1 power, but you're not able to solve the more complicated cases, right? Like where you raise something to more powers. Okay, so is everyone happy with this? Yeah, thanks. Okay, so let me say a word or two about derivatives of or integrals of exponential functions. I don't really have a lot to say, but I'll say what I can right now, and then yeah. So okay, really, the only thing that I can say about integrals of these exponential functions is that, okay, the integral, what is the integral? The definition of the integral is that if you have the integral of the derivative of some function, then you get back the function, right? Or this is the antiderivative. And so if we want to take the integral of the derivative and get back the function, we have that, okay, so let's start with e to the x. If we take the derivative of e to the x, we get e to the x. And so the integral of e to the x must just be e to the x, or the antiderivative, right? So now the same principle applies to all of these exponential functions. So the derivative of a to the x is equal to a to the x ln x. And we want to get back a to the x. And so then what we have to ask is what's the antiderivative? What can we put over here so that we get back a to the x? And so the answer is pretty simple. It's just a to the x over ln a, because then we get, when we take the derivative, the bottom is just a constant. So then we end up with a to the x ln a over ln a, okay? And then these two cancel and you just get back a to the x. Okay, so when I scroll down, I actually can't scroll. This is a whiteboard. But I can rewrite it or something if you can't see. So, oh, okay, great. Sorry about that. I'll try and write higher up if you, for some reason, can't see the bottom of the board. So, okay, that's really all I have to say about the integrals of these things. But if you want more, maybe you can tell me what you're looking for and I can try and say something next time. Okay, so let me talk a little bit about inverse functions. I know that we're going pretty fast today, but I'm trying to give you a bit of time to work on your quiz at the end. So inverse functions. The inverse of a function, so if f is a function, then the inverse of f is a function g, such that g of f of x gives you back x, okay? And so how do you know if a function has an inverse, right? Well, one thing that's very important is that in order to have an inverse, the function has to be one-to-one. And what this means is that if you plug in a value for x, there's exactly one value. So for every y that's in the output of the function, there's exactly one corresponding x that goes to y, okay? And why is this very important? Because say that you have two numbers that go to one number under some function. So let f be a function, and we'll define f so that it takes 1 and 2 both to 1, okay? So then what is the inverse function? So suppose that f has an inverse. What would the inverse function do? Okay, well, we know that g composed with f has to give you back the identity, right? So that means that g composed with f, if you put in 1, you have to get out 1, and g composed with f of 2 also has to give you 2, okay? And so let g be over here. So f does this, and what does g do? So then if g circ f of 1, by the way, this means function composition, so it's g of f of 1. So f of 1 gives you 1, and so that means g of 1 has to give you 1, okay? And f of 2 gives you 1, and so g of 1 has to give you 2. But wait, this is a big problem, because that means that g of 1 has 2 values. And you learned probably when you were younger that every function takes one value to one value. So this is not good, and it means that an inverse can't exist. So what does this mean practically for you when you're trying to figure out when a function has an inverse? Well, one thing that it implies is the horizontal line test. So say you want to figure out whether a function has an inverse. What you can do, if you are good at graphing or have a graphing calculator, is you can graph that function. And graphing the function gives you a very important piece of information, which is, so these are your y values, and these are your x values. And so if you just draw a horizontal line, what's this telling you? It's telling you all of the x values of the function that give you a certain y value, right? Oh, sorry, those are just the intercepts. But so what I meant to draw was, so this point gives you this y value, and the y value is also, you can get it from this point, and you can get it from this point as well, okay? And so the point here is that if you draw a horizontal line through the y-axis, then what happens is it intersects the graph of the function at all of the x values that correspond to that y value. And so if you have multiple x values or multiple intersections with that horizontal line, it means that your function can't possibly be invertible. Okay? Is everyone happy with this? Great. Oh. Is the function, so if a test question says, show that the function has an inverse. Oh, okay. Oh, that's a good question. Let me talk about that too. So in terms of the test question one, oh, okay. So this is what you'd want to do on a test question. I think the horizontal line test should probably be good. But the other thing that you can do that is better than the horizontal line test is you can just find the inverse, okay? And we'll talk about that in a second. But generally speaking, pictures are not the best way. It might be fine, I'm not sure, but pictures are not the best way. But if you can just find the inverse, then you're in better shape, because then you can just show, oh, look, like if you find your g, then you can just do g circ f is equal to x, and f's, and then there's nothing else to say, like you found the inverse, okay? So let me also say, let me address the vertical line test. So yeah, why can we not use the vertical line test to determine whether this function has an inverse? Well, I guess here's a counterexample. So the quick and dirty way of showing we can't do this is let's consider the function x squared, y equals x squared. Then draw a vertical line, okay? The vertical line only hits this function once, but this function doesn't have an inverse. And maybe an even better example is just take a horizontal line. So take the function y is equal to 3, okay? Then every value of x goes to the same value of y. The vertical line test passes through, only hits once. So it doesn't have an inverse, and the vertical line test won't tell you anything about inverses. Yeah, so but this is a good question. What is the vertical line test telling you? So like, what if you have something that has a graph like this, okay? Then if you draw the vertical line, it hits this spiral many times. So what this means is that for a given value of x, you're getting all these different y values. And so for simple functions like this, it means it's not really a function, right? Because if this were a function, one value of x gives one value of y, but here it's giving at least 6 or 7. So clearly the vertical line test is not quite what you want. Okay, great. So let me tell you how to find an inverse. In order to find an inverse of a function f, what you do is, if you have f of x, then so y is equal to f of x, then what you want to do to find the inverse is you flip x and y. So you say x is equal to f of y. And so then, once you've done that, you want to solve for your value of y, okay? And then you end up getting the inverse. Yeah? So the reason that this works, at least morally, is that this function is telling you, given a value of x, what value of y do you get? And if you resolve this equation for y, then what you're saying is, for a value of y, what value of x do you get, okay? And so this is what you want for the inverse function. Okay, so let me give a quick example. Suppose you have something like x cubed plus 1, y equals x cubed plus 1. Let's draw the graph for this function to check it has an inverse. By the way, you should always use the horizontal line test before you start trying to find an inverse, because if you start trying to find an inverse, sometimes it gets messy and hard. And so if you draw the line first, you know that it exists and you won't be wasting your time. Okay, so this is what the graph looks like. Do the horizontal line test and see it has an inverse. So let's prove it. We can rewrite x equals y cubed plus 1. So then we get x minus 1 equals y cubed. And because cubes are invertible, we can just do y is equal to x minus 1 to the 1/3, okay? And then let's check that this is truly an inverse. So we have to compose these functions. So we'll call this thing g of x, and we'll call this thing f of x. And then if we do f of g of x, then we get x minus 1 to the 1/3 cubed plus 1. We get x minus 1 plus 1. Oh, sorry, I'm writing too low again. And then we get x, okay? So that's the horizontal line test. Okay, one more thing. We didn't get through my whole lesson plan, but you'll have a bit of extra time to do your quiz. So let me show you how to take the derivative, because probably your next classes don't start until 11, so then you'll have 25 minutes. Okay, so suppose that we want to take the derivative of the inverse function. So you're given f, you want to find the derivative of its inverse, okay? So how do we do this? Again, this is something that people memorize formulas for, but it's really unnecessary. What you have to do, insight, is that f of f inverse of x is equal to x. So now let's take the derivative on both sides. The right side gives you 1. The left side gives you, by the chain rule, f prime of f inverse of x times, okay, derivative of the inner function, that's f inverse of x prime. Okay, so this is exactly what we want. So what do? We just divide. We get f inverse of x prime is equal to, so divide out by this thing, 1 over f prime f inverse of x. Okay, and that's your formula that you maybe memorized in the past. Okay, so I think because I was instructed to give you some time to try and do the quiz, I'm going to stop here. But you have two options. If you want to go through some of the examples in more detail, you can watch my Thursday video, or you can do them in the privacy of your own home, because all of the examples that I was going to give are also on this sheet. What lectures does the quiz cover? I don't know, I haven't seen it. But I think we're up to speed now, right? Does taking the derivative to prove the horizontal line test always work? Let me think about that for a second. Okay, so I think probably the professor's, okay. So I think the professor's point is probably that, so what does the derivative tell you, right? The derivative tells you that a function, it tells you the rate of change of a function, right? So if this is your rate of change at this point, and this is your rate of change at this point, what can we say about the inverse? So if the rate of change of a function switches signs, meaning that if the derivative is positive here and negative here, then that means that the function isn't going to have an inverse here, because the problem is if your function increases and then decreases, that means it necessarily has to cross the same point twice, right? And so I think probably the professor's point was that one thing that you can maybe do to try and figure out if there's an inverse is you can take the derivative at a bunch of points, or you can take the derivative of the function. You can find out the points where that function is 0. And then once you've found the points where that function is 0, you can look a little bit to the left and a little bit to the right of those points and figure out if the derivative switches signs. Because if it switches signs, then there's not going to be any inverse. So for example, like this function's a cubic. Take the derivative here and it's 0. And then you can look on either side, but you see the derivative is positive either way. So you're good to go. This one can still have an inverse. But oops. If you look at something like this, and you take the derivative here, you see it's 0. And then you look on either side, here it's positive, here it's negative. And so this thing doesn't have an inverse. And one way you can show that a function does have an inverse, I guess, is if you take the derivative and it always has the same sign, then that means that the function is going to have an inverse. Okay? Cool. All right. Well, I'll see you next week and good luck on your quiz.